Week 5 Hypothesis Testing. Welcome back, everyone. This is Week 5, and our topic is hypothesis testing. Here is a quick honesty check for you. If last week felt heavy, today should feel more like relief than a new mountain to climb. We are not learning a brand new set of machinery from scratch. We are taking the exact same Z and T tools you already built last week and pointing them at a new, genuinely practical kind of question. This slide lists 9 specific objectives, and I am going to translate that whole list into one plain sentence for you right now. By the end of today, you will be able to take a yes or no business claim, something like, the average is exactly this number, and turn it into a formal, structured test. You will run the numbers using either Z or T, and you will state your conclusion in plain English, that you would be comfortable defending out loud to a partner at your firm or to a regulator asking hard questions. There is one line on this slide worth saying slowly, because it is genuinely the entire week summarized in 2 sentences. Last week, we estimated an unknown parameter using a confidence interval. This week, we test one specific claim about that parameter directly. Same underlying engine, just a sharper, more pointed question. Let's do 3 quick reminders before we move forward. First, X bar, the sample mean, behaves like a random variable. It has its own entire sampling distribution attached to it. Second, the central limit theorem tells us that once our sample size n is 30 or more, X bar is approximately normal in shape. Third, we built confidence intervals last week, which are ranges of plausible values for the unknown mu, using either Z or T depending on what we knew about sigma and how large our sample was. Here is the bridge connecting last week to today, and it is worth repeating because it really is the whole lecture compressed into 2 sentences. A confidence interval asks, given my sample, what entire range of values is plausible for mu? A hypothesis test asks a sharper question. Given my sample, is one specific claim about mu actually believable? Same data, same underlying tools, just a more pointed question being asked of them. Let's move into Part A. Welcome to Part A, the logic of hypothesis testing. Brand new vocabulary starts right here, including the terms H0, H1, and the 2 distinct kinds of error we can make. Business and accounting questions are usually framed as yes or no claims about an entire population. Is the mean error rate on invoices really below 5%? Has average daily revenue actually increased since a new marketing campaign launched? Is the mean reporting delay for listed companies really no more than 15 days? We can never answer questions like these with total, absolute certainty because we only ever have a sample in front of us, never the entire population. But hypothesis testing gives us a defensible, repeatable, professionally accepted way to make that call anyway, despite that uncertainty. Think about how a compliance officer actually works in practice. She cannot personally recheck every single transaction a company made over an entire year. That would take far too long. But she can still make a defensible, evidence-based judgment from a carefully chosen sample of those transactions. That is precisely the position we are in today, every time we run a hypothesis test. Let's meet the 2 competing claims that sit at the center of every single test. Every hypothesis test starts with 2 competing statements, and the vocabulary here genuinely matters, so let's be precise about it. The null hypothesis, written H0, is the no change, nothing unusual going on here claim. It always contains an equals sign somewhere in it. The alternative hypothesis, written H1, is the claim we are actually investigating, what we suspect might be true instead of the status quo. It contains not equal to, less than, or greater than. Here is one detail that trips people up immediately, so let's be precise about it. Both hypotheses are statements about the population parameter, mu, never about our sample statistic, X bar. We are never testing what our sample actually showed. We already know that number with certainty. We are testing what it is reasonable to believe about the entire population that sample came from. There are 3 shapes this question can take. A 2-tailed test asks whether mu is different from some claimed value, in either direction at all. A left-tailed test asks specifically whether mu is less than some claimed value. A right-tailed test asks specifically whether mu is greater than some claimed value. Let's see this play out with some real numbers. Let's go through 3 quick scenarios, purely to build the habit of translating an English sentence into H0 and H1 correctly. Scenario 1. An audit firm claims its mean tax return processing time is 2.5 days, and we want to test whether it is actually different from that in either direction. That is a 2-tailed test. H0 mu equals 2.5, H1, mu is not equal to 2.5. Scenario 2. A chief financial officer claims that new staff training has reduced the mean error rate, which was originally 5%. The word reduced means we are specifically testing for a decrease, so this is a left-tailed test. H0, mu is greater than or equal to 5. H1, mu is less than 5. Scenario 3. Has the regulator's mean reporting delay increased above 15 days? The word increased signals a right-tailed test. H0, mu is less than or equal to 15. H1, mu is greater than 15. Here is a shortcut genuinely worth writing down somewhere. The words different or changed signal a two-tailed test. The words less, decreased, or reduced signal a left-tailed test. The words greater or increased signal a right-tailed test. Learning to spot these keywords quickly is honestly half the battle on any exam question involving hypothesis testing. Are you ready for what is probably the single most important idea in this entire lecture? Here's the logic that makes everything else in today's lecture make sense, so let's go through it slowly. Picture a courtroom trial. The defendant is presumed innocent from the very start, and that presumption of innocence is our H0. The prosecution must present strong, convincing evidence to overturn that presumption, and that evidence is our sample data. If the evidence turns out to be convincing enough, the jury convicts, and in our world, we reject H0. If the evidence falls short of that bar, the jury delivers a verdict of not guilty, and in our world, we fail to reject H0. Now here is the sentence I genuinely need you to sit with for a moment. A verdict of not guilty does not prove that the defendant is actually innocent. It only means the evidence presented was not strong enough to convict them beyond a reasonable doubt. In exactly the same way, failing to reject H0 never proves that H0 is true. It only means our particular sample did not give us strong enough evidence to throw H0 out. This is exactly why you will never, ever hear a properly trained statistician say, "We accept H0." We only ever say, "We reject H0" or "We fail to reject H0", and that small difference in wording carries real, meaningful weight. Are you sitting comfortably with this courtroom picture? Good. Now let's talk about exactly what can go wrong with a verdict. Every single test can go wrong in exactly two distinct ways, and giving each one a name lets us reason about them precisely instead of vaguely. A type 1 error means rejecting H0 when it was actually true all along. Statisticians often call this a false alarm. A type 2 error means failing to reject H0 when it was actually false all along. This one is a misdetection. Think about how a household smoke detector behaves. It's sounding the alarm when there is no fire at all anywhere in the house is a type 1 error, annoying and a little costly in lost sleep, but not actually dangerous. It's staying completely silent during a real, genuine fire is a type 2 error. And that one can genuinely hurt someone. Here is a second, equally vivid picture. A doctor telling a perfectly healthy patient that they are sick is a type 1 error. A doctor telling a genuinely sick patient that they are fine is a type 2 error. Most people's gut instinct is that the second mistake feels considerably worse than the first, and that instinct is usually correct, which is exactly why we will see auditors deliberately design around this asymmetry in just a moment. One more useful term while we are here. The power of a test is 1 minus beta, the probability of correctly catching a false H0 when it really is false. A more powerful test is simply a more alert smoke detector, one that is genuinely more likely to catch a real fire when one is actually happening. Are you clear on both kinds of error now? Let's see why auditors specifically care about this particular distinction. Let's make this fully concrete, entirely in our own world. An auditor tests whether the mean error rate on a company's invoices exceeds 5%, the materiality threshold for this engagement. H0, mu is less than or equal to 5. H1, mu is greater than 5. A type 1 error here means concluding that the error rate is too high when it really is not. The consequence is unnecessary extra audit work, wasted professional fees, and a damaged relationship with the client. Costly, certainly, but ultimately recoverable. A type 2 error means concluding the error rate is acceptable when it is actually too high. The consequence here is far more serious. An undetected material misstatement slipping through, a failed audit, and real professional liability landing on the auditor's shoulders. That underlying asymmetry between the two consequences is precisely why auditing standards set alpha at a relatively generous 5%, or sometimes even 10%, rather than squeezing it down as small as mathematically possible. A slightly higher chance of a false alarm is simply the price worth paying to keep the far more dangerous misdetection error small. Are you comfortable with that trade-off? Let's put an actual number on alpha. Alpha, the significance level, is the chance of a type 1 error that we are willing to tolerate, and critically, this number is decided before we ever even look at the data. 3 values come up constantly in practice. 0.10 gets used in exploratory studies where there is a high tolerance for false alarms. 0.05 is the standard across business and the social sciences generally, and 0.01 is reserved for especially critical decisions, like medical or pharmaceutical research, where the stakes of a false alarm or a misdetection are both extremely high. Unless a question explicitly tells you otherwise, the default you should reach for is alpha equals 0.05. Lock that number into memory, because it covers the overwhelming majority of what we are going to do for the rest of today. Now let's see exactly how alpha carves up the bell curve itself. The shape of our rejection zone, the range of test statistic values that would lead us to reject H0, depends entirely on which kind of H1 we wrote down earlier. For a two-tailed test, the rejection territory sits in both tails of the curve at once. At alpha equals 0.05, that means we reject H0 if our z-value falls beyond plus or minus 1.96, with 2.5% of the probability tucked away into each tail. For a right-tailed test, all of the rejection territory sits in the right tail alone, and we reject if z exceeds 1.645. For a left-tailed test, it is the mirror image of that, and we reject if z falls below negative 1.645. Think about a security checkpoint with one fixed, alpha-sized suspicion budget to spend on flagging travelers for extra screening. A two-tailed test splits that budget evenly between both ends of some scale. A one-tailed test spends the entire budget watching just one single end of that scale, which naturally makes it more sensitive at that one end. Are you following the shift in shape here? Let's lock in the exact numbers properly. This is a reference table genuinely worth memorizing, not just glancing at once and forgetting. It lists the critical value, the exact boundary number, read from a table that marks where our rejection zone actually begins for each common alpha level. At alpha equals 0.10, the one-tailed critical z is 1.282, and the two-tailed value is 1.645. At 0.05, the one-tailed value is 1.645, and the two-tailed value is 1.96. At 0.01, the one-tailed value is 2.326, and the two-tailed value is 2.576. Here is the detail that trips up almost everyone the very first time they see this table. For alpha equals 0.05, the two-tailed critical value, 1.96, is actually larger than the one-tailed value, 1.645. That happens because the exact same total alpha budget gets split across two separate tails instead of being concentrated entirely into one. This whole table is genuinely worth copying into your own notes for quick reference later. Are you ready to put the z-test to actual work? Welcome to Part B. The z-test for a single population mean. This is the same standardizing move you learned back in week 3 and week 4, now aimed squarely at testing a specific claim instead of simply describing a value. The one sample z-test applies whenever we are testing a hypothesis about a single mu, and either sigma is already known to us, or our sample size is 30 or more, which lets S safely substitute in for sigma. Our test statistic, the single number we calculate from our sample and then compare directly against a critical value, looks exactly like the standardizing formula from week 3. There is one small twist to notice here. Z equals x bar minus mu 0, divided by sigma over the square root of n. Notice that mu 0 specifically, that is the hypothesized value taken straight from H0, not the unknown true mu we are ultimately chasing after. Under H0, this z statistic follows the exact same standard normal distribution we already know well from previous weeks. That is really the entire trick behind hypothesis testing. Assume H0 is true for a moment, see how unusual our actual sample would look under that assumption, and let that level of unusualness tell us whether we should keep believing H0 or abandon it. Are you ready for the procedure we are going to reuse over and over again for the rest of today? Every single hypothesis test in this entire course, whether it uses Z or T, whether it is one sample or two sample, follows the exact same 5 steps, every time without exception. Step 1. State H0 and H1, and identify which tail type you are dealing with. Step 2. State alpha, usually 0.05 unless told otherwise. Step 3. Identify the test statistic you need and look up its critical value. Step 4. Compute the test statistic from your actual sample data. Step 5. Make a decision and interpret that decision in plain English. Think about this the same way an airline pilot thinks about a pre-flight checklist. The exact same items get checked in the exact same order on every single flight, regardless of the destination, the weather, or how experienced the pilot is. Once these 5 steps become automatic for you, every hypothesis test in this entire course collapses down into the same short, familiar routine. Let's run that routine on a real problem together, right now. An audit firm claims its mean tax return processing time is 2.5 days, with sigma known to be 0.6. A sample of 36 returns gives X bar equal to 2.7 days. At alpha equals 0.05, is the mean actually different from 2.5? Step 1. H0 mu equals 2.5. H1 mu is not equal to 2.5. This is two-tailed because we are testing for any difference at all, not specifically a higher or specifically a lower value. Step 2. Alpha equals 0.05. Step 3. For a two-tailed test at this alpha level, our critical values are plus or minus 1.96. We will reject H0 if our calculated Z falls beyond either of those two boundaries. The setup is complete, so let's move on to computing the actual numbers. Step 4. The actual computation. The standard error is the typical size of the gap we would expect between a sample mean and the true population mean, purely from ordinary random sampling, and it equals sigma over the square root of n. 0.6 divided by the square root of 36, and the square root of 36 is exactly 6, gives us 0.1. Now we standardize. Z equals x bar minus mu 0, divided by that standard error we just calculated. That is 2.7 minus 2.5, divided by 0.1, which works out to exactly 2.00. Step 5. The decision. Since 2.00 is greater than 1.96, we reject H0. In plain English, at the 5% significance level, there is sufficient evidence that the mean processing time differs from 2.5 days, and the sample specifically suggests the true mean is actually higher than claimed. Notice that we followed the exact 5-step checklist from the previous slide, start to finish. Are you ready for a right-tailed version of the exact same idea? Here is a new scenario, this time right-tailed. The exchange regulator expects mean audit adjustments per listed company to be no more than 8. A sample of 49 companies gives X bar equal to 9.2, with sigma equal to 3. At alpha equals 0.01, has the figure actually increased? Step 1. H0 mu is less than or equal to 8. H1 mu is greater than 8. This is right-tailed, since the word increased points in exactly one direction. Step 2. Alpha equals 0.01. Step 3. The critical value for a right-tailed test at this alpha is 2.326. We reject H0 if our Z exceeds that value. Step 4. The standard error is 3 divided by the square root of 49, and the square root of 49 is 7, giving 0.4286. Z equals 9.2 minus 8, divided by 0.4286, which works out to approximately 2.80. Step 5. Since 2.80 exceeds 2.326, we reject H0. At alpha equals 0.01, there is sufficient evidence that mean audit adjustments genuinely exceed 8. Are you following each step comfortably so far? There is a second, equally valid way to arrive at this exact same conclusion. Everything we have done so far has used the critical value approach, which simply asks whether our test statistic landed inside the rejection zone or not. The p-value approach asks that identical underlying question in a slightly different language. How probable would a result at least this extreme actually be if H0 were genuinely true? Formally, the p-value is the probability, assuming H0 is true, of getting a test statistic at least as extreme as the one we actually calculated. measured in the direction h1 points toward. The decision rule here is refreshingly simple. If the p-value is smaller than alpha, reject h0. If it is at least as large as alpha, fail to reject h0. Think of the p-value as a kind of built-in surprise meter. A tiny p-value is telling you, if h0 were really true, what you just observed would be wildly surprising, and wildly surprising results naturally make us start doubting h0. A large p-value is telling you the opposite. This would be a perfectly ordinary, unremarkable result under h0. Nothing here worth doubting at all. Are you ready to actually compute one of these yourself? The exact recipe for computing a p-value depends entirely on which tail type you are dealing with. For a right-tailed test, the p-value is the probability that z exceeds our calculated value. For a left-tailed test, it is the probability that z is below our calculated value. For a two-tailed test, you double whichever one-tailed probability you get, since either extreme in either direction counts as evidence against h0. Let's revisit worked example 1 from earlier, our two-tailed test where z equaled 2.00. Looking this up in the z table, the probability that z exceeds 2.00 is 1 minus 0.9772, which equals 0.0228. Doubling that number, since this is a two-tailed test, gives us a p-value of 0.0456. Since 0.0456 is less than 0.05, we reject h0, which is exactly the same conclusion the critical value approach gave us earlier. Notice that neither approach is somehow more correct than the other. They are simply two different languages describing the exact same underlying evidence. This deserves to be stated explicitly and clearly. The critical value approach and the p-value approach will always agree with each other every single time for the same test run at the same alpha level. One approach compares your test statistic directly to a critical value. The other compares your p-value directly to alpha. Same underlying evidence, same final verdict, just different vocabulary describing it. So which one should you actually report in practice? Modern statistical practice generally favors reporting the p-value because it tells you how strong the evidence actually is, not merely whether it crossed some fixed line in the sand. A p-value of 0.04 and a p-value of 0.0001 both lead you to the same decision, reject, but the second one is dramatically more convincing evidence than the first, and that distinction matters in a real report. Every piece of statistical software you will ever use reports the p-value automatically, without you even asking for it. Are you comfortable with both languages now? Let's go meet the t-test. Welcome to Part C, the t-test for one population mean. Same 5-step procedure, same underlying logic. We are simply swapping tools for the situation where sigma is unknown and our sample is small. The one-sample t-test applies when we are testing a single mu, sigma is unknown, and our sample size is below 30. The test statistic looks almost identical to the z-test formula. T equals x bar minus mu 0, divided by s over the square root of n. We have simply swapped the unknown sigma out for our sample's own s. Under h0, this statistic follows the student's t-distribution, a bell-shaped curve that looks close to the normal curve but a little flatter in the middle, with heavier tails out at the edges. Its exact shape depends on the degrees of freedom, a number reflecting how much genuinely independent information our sample actually provides, equal to n-1 here. Remember from last week that flatter, heavier-tailed shape makes the t-test a touch more conservative than the z-test at the same alpha level. Think about the difference between trusting a brand new employee's time estimate for a task versus a 20-year veteran's estimate for that exact same task. The newer employee's estimate carries more built-in uncertainty, simply from having less experience to draw on, so you naturally want a wider safety margin around whatever number they give you. That extra margin is exactly what the t-distribution builds in automatically. Let's pin down precisely when each tool applies. Here's one clean decision rule, genuinely worth memorizing completely, because you will use it constantly. If sigma is known, use z, no matter how large or small your sample size happens to be. If sigma is unknown, but n is 30 or more, you can still safely use z, simply substituting s in for sigma. If sigma is unknown and n is below 30, use t, with degrees of freedom equal to n-1. This is the exact identical rule we learned for building confidence intervals last week, simply carried over now to hypothesis testing instead. Same underlying decision, Same underlying logic, just a new application of it. Here is a worked reference table, so you can see the pattern clearly before we use it for a real problem. For a two-tailed test with n equals 15 at alpha 0.05, the degrees of freedom is 14, and the critical t is plus or minus 2.145. With n equals 20 at that same alpha, degrees of freedom 19 gives plus or minus 2.093. With n equals 25 at alpha 0.01, degrees of freedom 24 gives plus or minus 2.797. For one-tailed tests, a right-tailed test with n equals 16 at alpha 0.05, degrees of freedom 15 gives a critical t of positive 1.753. A left-tailed test with n equals 12 at that same alpha, degrees of freedom 11 gives negative 1.796. Remember how to read this kind of table from last week. Rows represent degrees of freedom, columns represent tail area, the exact same Harbor tide chart logic we used before. Are you ready to run a full t-test from start to finish? An audit firm reports that its mean fee per engagement is 12,000 ringgit. A sample of 16 engagements gives X bar equal to 13,200 ringgit, with S equal to 2,400. At alpha equals 0.05, has the mean fee actually changed? Step 1. H0 mu equals 12,000. H1 mu is not equal to 12,000. Step 2. Alpha equals 0.05. Step 3. Sigma is unknown, and n equals 16, below 30, so we use t with 15 degrees of freedom. The critical values are plus or minus 2.131. Step 4. The standard error is 2,400 over the square root of 16, which is 4, giving 600. Then t equals 13,200 minus 12,000, divided by 600, which equals 2.00. Step 5. Since 2.00 is less than 2.131, we fail to reject H0. In plain English, there is insufficient evidence that the mean fee differs from 12,000 ringgit. Notice that this is a different verdict from worked example 1 earlier, even though it involves the identical looking number 2.00. Here is exactly why that matters. Let's look at the exact same numbers from the example we just finished, viewed two different ways. As a z-test, if sigma really were known with certainty to be 2,400, our z of 2.00 would exceed 1.96, and we would reject H0. As a t-test, with s merely estimated at 2,400 instead of known outright, our t of 2.00 falls just short of 2.131, and we fail to reject. Why does this disagreement happen? The t-test is simply more conservative by its very nature. The heavier tails of the t-distribution reflect the genuine extra uncertainty that comes from estimating sigma using s, rather than knowing its true value outright. This is not a flaw, and it is not a contradiction. It is the t-distribution doing exactly the job it was designed for, building in a margin for what we genuinely do not know for certain. Are you sitting comfortably with why these two approaches can differ from each other? Let's try a left-tailed t-test next. A manufacturer claims its mean number of defects per production batch is 4 or more, but the quality control manager suspects the true figure is actually lower than that. A sample of 25 batches gives X bar equal to 3.2 with S equal to 1.5. Test at alpha equals 0.05. Step 1. H0 mu is greater than or equal to 4. H1 mu is less than 4. This is left-tailed, since the word lower points in exactly one direction. Step 2. Alpha equals 0.05. Step 3. We use t with 24 degrees of freedom. The critical value is negative 1.711, and we reject H0 if our t falls below that value. Step 4. The standard error is 1.5 over the square root of 25, which is 5, giving 0.3. Then t equals 3.2 minus 4, divided by 0.3, which works out to approximately negative 2.67. Step 5. Since negative 2.67 is below negative 1.711, we reject H0. There is evidence that the mean number of defects per batch genuinely is below 4, which is good news for that quality control manager. Here is one more full worked example, this time pairing the t-test together with its p-value. An audit firm claims its mean internal control review time is 20 hours or less. A sample of 12 reviews gives X bar equal to 22.5 hours, with S equal to 4.2. Test at alpha equals 0.05. For the setup, H0 mu is less than or equal to 20. H1, mu is greater than 20. We use t with 11 degrees of freedom. The critical value is 1.796. For the computation, the standard error is 4.2 over the square root of 12, which is approximately 1.213. Then t equals 22.5 minus 20, divided by 1.213, which works out to approximately 2.06. For the decision, since 2.06 exceeds 1.796, we reject H0. For the matching p-value, the t-table shows that a t of 1.796 corresponds to a tail area of 0.05, while a t of 2.201 corresponds to 0.025. Our calculated t of 2.06 sits between those two values, so our p-value falls somewhere between 0.025 and 0.05. Excel would actually give us the precise figure directly, approximately 0.032. Let's talk about how to write all of this up properly. A complete professional write-up of any hypothesis test should always include 6 things: the hypotheses themselves, which test was used and with what degrees of freedom, the value of the test statistic, the critical value or the p-value, the final decision, and a plain English interpretation of what that decision actually means. Here's how that reads in practice, using the audit fee example from worked example 3. A two-tailed one-sample t-test with 15 degrees of freedom was conducted to determine whether the mean audit fee differs from 12,000 ringgit. From a sample of 16 engagements, with X bar equal to 13,200 ringgit and S equal to 2,400, the test statistic was T equals 2.00. This did not exceed the critical value of plus or minus 2.131 at alpha equals 0.05, so we failed to reject the null hypothesis. We conclude there is insufficient evidence that the mean audit fee differs from 12,000 ringgit. That paragraph is genuinely your template going forward. Memorize its overall shape, not its specific numbers. Let's move on to comparing two groups at once. Welcome to part D, comparing two means at once, plus running all of this directly in Excel. So far, every single test we have run has compared one sample mean against one fixed number. Many real-world questions instead compare two entire groups directly against each other. Are audit fees genuinely different between large firms and small firms? Did a new computer system actually reduce mean processing time compared to the old system? Is mean monthly revenue genuinely higher in one region than in another? For two independent samples, we test H0, the claim that the two population means are equal. Our test statistic is T. We find it by taking the difference between the two sample means, x bar 1 minus x bar 2, and dividing that by the square root of s1 squared over n1 plus s2 squared over n2. For hand calculations, a conservative estimate of the degrees of freedom is simply the smaller of the two sample sizes, minus 1. Statistical software instead uses a more precise but considerably messier method called Welch's approximation, a formula that adjusts the degrees of freedom to account for the two groups potentially having different amounts of spread. Think about comparing the average wait time at two different coffee shops on the same street to see whether one is genuinely, reliably faster than the other, rather than just having gotten luckier on the particular days you happen to visit and time it. Are you ready to run the full numbers on a real example? An audit firm wants to compare completion times at two of its branch offices. At the first office, 25 files were sampled, giving a mean of 38 hours with a standard deviation of 6. At the second office, 20 files were sampled, giving a mean of 42 hours with a standard deviation of 7. At alpha equals 0.05, do the two offices genuinely differ from each other? Step 1. H0. The two population means are equal. H1. They are not equal. This is two-tailed. Step 2. Alpha equals 0.05. Step 3. Our conservative degrees of freedom is the smaller sample size minus 1, 20 minus 1, which is 19. The critical value is plus or minus 2.093. The setup is complete, so let's finish the arithmetic. Step 4. First, the standard error. We take the square root of 6 squared over 25 plus 7 squared over 20. That is the square root of 1.44 plus 2.45, which is the square root of 3.89, approximately 1.972. Then the test statistic itself, 38 minus 42 divided by 1.972, which works out to approximately negative 2.03. Step 5. Since the size of negative 2.03, ignoring the sign 2.03, is less than 2.093, we fail to reject H0. In plain English, at the 5% significance level, there is insufficient evidence of a genuine difference in mean completion times between the two offices. It is worth noting that this particular result is fairly borderline, close enough that a slightly larger sample at either office could easily have tipped the conclusion the other way. Let's imagine this scenario. You manage a light bulb factory. The machines are calibrated so that the average lifespan of a batch should be 12,000 hours. You suspect a new filament formula makes the bulbs last significantly longer than 12,000 hours. You test a sample of 16 bulbs. For comparing two groups directly, Excel's t-test function takes both of your data ranges, plus two extra settings, tails and type. Tails is either 1 or 2. Type is where 1 means paired data, 2 means 2 independent samples assumed to have equal variance, and 3 means 2 independent samples with unequal variance using that Welch's adjustment we just discussed. For most real independent 2-sample situations you will encounter, type 3 is the genuinely safer default to reach for. While the previous manual setup was for a 1-sample t-test, comparing one group against a fixed number like 12,000, the equals t-test function is designed for a 2-sample t-test. It bypasses the need to calculate t-statistics and degrees of freedom altogether, directly returning the final p-value by comparing 2 separate sets of data. To use the exact same light bulb data from the previous example, we will introduce a second group, e.g. bulbs from an older manufacturing machine, to see if the new machine's bulbs perform significantly differently. The output is your final p-value. Because 0.000021 is vastly smaller than the standard significance threshold of 0.05, you reject the null hypothesis. Let's compress today's 9 ideas into one pass. We set up H0 versus H1 and asked whether our observed data looked unusual under the assumption that H0 was actually true. We named type 1 error a false rejection governed by alpha, and type 2 error, a misdetection governed by beta. We learned the Q words. Different signals a 2-tailed test, less or greater signal a 1-tailed test. We applied the exact same 5-step procedure to every single test we ran. We used the z-test when sigma was known or n was 30 or more, and the t-test when sigma was unknown and n was below 30. We extended this framework to comparing 2 independent means at once. We confirmed that the critical value approach and the p-value approach always agree with each other, and we ran all of it in both Excel and SPSS. Here's the single thread running through everything we covered today. A hypothesis test simply asks how surprising your sample would be if the claim you are doubting were actually true. And surprising enough to doubt it is a line we draw deliberately before we ever look at the data itself.